In computational dynamics, discrete mathematical approximations usually converge as resolution increases, but on the exact boundary of an otherwise stable parameter space, a violently diverging numerical anomaly suddenly emerges. The environment producing this anomaly is a set of twisted transfer operators on the interval from -3 to +3. Here, three specific kernels, WBA, Lorentzian, and alien, operate within a strict rigidity window between epsilon 0.70 and 1.10. Previous research ran a spike quotient battery across 4 successive grid doublings within this window. The results split the kernels into a strict 2-class discrete taxonomy. The first class is B1 coherent. This encompasses 5 separate kernel configurations, where discrete width proxies remain tightly bounded and mathematically stable across all computed resolutions. The second class contains exactly one configuration, the WBA kernel at epsilon 0.70. This represents the anomaly, a B2 entropic spray, where the entropic width proxy grows monotonically with every single grid doubling. This isolated divergence prompts a highly specific question. What exact discrete numerical mechanism drives this isolated B2 entropic spray? To find the answer, we test 2 structural possibilities. Either the Ulam transition matrix inherently couples cells in a heavier-tailed way, or the matrix structures are actually similar, and the heavy tail is purely a feature of how the resulting eigenvector distributes its mass. This investigation operates under strict methodological constraints. No new computations are performed. Every finding relies entirely on data from 2 locked files, a 21-row n-scan matrix, and a 2-row off-diagonal probe. Because these tests evaluate finite grid discretization artifacts, they map the bounds of a numerical environment and make no claims regarding the continuous continuum. Isolating the mechanical source of this spray is the only way to separate actual dynamical properties of the system from the numerical viscosity effects inherent to Ulam discretizations. The first phase of this test requires mapping the exact trajectory of the anomaly as we systematically increase the resolution. We extract data across 4 executed Ulam-grid doublings, n equals 2048, 4096, 8192, and 16384. This log-log chart maps our baseline behavior. The bounded variation proxy remains tightly constrained. As resolution doubles, data points never leave this narrow band between 3.10 and 3.35. The entropic proxy diverges immediately, plotting well above the band at 165. At n equals 4096, it climbs to 359. At 8192, it reaches 529. The upward trajectory continues without interruption. By the final grid point at 16,384, the entropic proxy hits 863. This establishes a strictly monotonic, unsaturating growth pattern. To understand the severity of this divergence, we measure the logarithmic divergence ratio between the proxies, which strictly rises from 1.704 to 2.426. Drawing a best-fit line through the 4 points yields an empirical power law, approximately 0.5072 times n to the power of 0.7715. That exponent lies within 3% of the rational fraction 3/4. However, a 4-point regression cannot resolve an exact fractional limit, making this a structural observation. We can compare this specific trajectory against the stable B1 coherent cells to illustrate just how unique the anomaly is. Overlaying the Lorentzian baseline data reveals a cluster of flat, non-monotone points hovering near the bottom of the graph.
This stark visual contrast definitively confirms the B2 spray classification on the executed grids. There is no visible mathematical saturation or leveling off across the computed doublings. We must recognize the grid-scoped limitations. This power law is a finite numerical observation, not an asymptotic proof of how the system behaves at infinity. Because the entropic tail's growth follows a systemic, unyielding power law, it demands an equally massive structural cost. That leads to the Ulam matrix hypothesis. The logical assumption is straightforward. If the eigenvector exhibits a radically heavier-tailed spray, the discrete transfer matrix generating it must possess a heavier-tailed off-diagonal structure. To test this, we use a direct structural probe to evaluate the column Shannon entropy of the matrices at a fixed resolution of 1024. We extract 3 specific metrics: the mean column Shannon entropy, the relative entropy, and the tail mass fraction. These side-by-side heat maps show the WBA and Lorentzian Ulam matrices. Despite the massive behavioral divergence dictated by the power law, the two matrices are structurally indistinguishable. The mean column Shannon entropy values show near-perfect alignment, 6.8858 versus 6.8846. Their relative entropies match exactly to 4 decimal places. We then apply a strict bandwidth constraint, carving out a diagonal band of 51 selves, exactly 5% of the matrix. This narrow band holds a minor fraction of the data, leaving the vast majority off diagonal. Comparing the tail fraction shows that over 90, every row couples to nearly every column, making both Ulam matrices effectively full. This null result decisively eliminates gross off-diagonal transition mass topography as the driver of the B2 spray on these grids. We are left with a strict paradox. We have an unyielding empirical power law driving growth, yet the foundational matrices generating it are structurally identical. By process of elimination, we localize the true mechanism. The spray is not encoded in the matrix itself. It is an artifact of pure eigenvector concentration. As grid resolution grows, the WBA eigenvector distributes its complement mass across an ever-widening array of cells. Isolating this behavior dictates the exact target for the next stage of research, slated for paper 50. Those tests will use a direct cumulative mass curve probe to quantify this exact eigenvector spreading by tracking how the mass fractions behave as n scales up. But for this study, strict mathematical guardrails apply to all findings. The power law is purely a numerical regression on the executed grids. It is not a certified limit as n approaches infinity. Likewise, the bounded nature of the variation proxy remains a discrete observation, not a formal convergence proof. Prior proofs from paper 37 have already certified that the true continuous invariant density is bounded variation with a confirmed spectral gap. Therefore, any unsaturating divergence observed here must be interpreted strictly as a numerical viscosity effect. The anomaly is definitively isolated to finite grids.